Okay. All right. Technical difficulties resolved. So today I wanted to work another example problem or two with you guys, and then we will move on to multi-frequency circuit analysis, which we will find out is just effectively the same thing, but we have to work the problem twice. So let's say that we have the following circuit. And we're just going to start with this guy in the frequency domain. So we have a 12 angle 0 degrees volts RMS source. We have a generic impedance, which I'm going to call 3 plus J2 ohms, through which I am trying to find the phasor current I. I have a J3 ohm impedance, a 6 angle 0 degrees voltage source, a 4 ohm impedance, minus J2 ohm impedance, and a 3 angle 10 amp source. All right, so obviously we could solve this circuit using either nodal analysis or mesh analysis, because the calculators that you're allowed to use in this class for exams are incapable of solving a system of equations involving complex numbers. Let's work this problem as if it were given to us on a test, where we're just going to have to rely on techniques like KCL, KVL, Ohm's law, source transformation, voltage division, current division, Thevenin and Norton equivalent circuits, etc. How do you think we might go about solving for the quantity phasor current I? Cheston.
You do a source transformation on that current source, and you just do a KCO equation at that node that I kept leaving.
Okay, so the suggestion here is that we have a practical current source on the right-hand side containing a 3 angle 10 degrees amp source in parallel with a minus J2 ohm impedance. If we do a source transformation, that's going to convert into a voltage source in series with that minus J2 ohm impedance. And that minus J2 ohm impedance will then be in series with the 4 ohm impedance, so we could combine that, and effectively we would have a circuit where we have 3 voltage sources, all of whose negative polarity terminal would be connected together at the bottom. And we'd only have 3 impedances. So yeah, we'd only have one really unknown quantity, the voltage present at the node connecting the 3 plus J2 ohm impedance, the J3 ohm impedance, and what is currently just the 4 ohm impedance. Yeah, that seems perfectly reasonable. Okay. So let's do just that. I'm going to redraw everything that I'm not changing. And then Cheston, since you suggested this methodology, I would like for you to tell me what the results of my source transformation are supposed to be.
Result of the source transformation,
Yes, sir.
just the two angle 10, or would you just add it to like 90 degrees?
You wouldn't add or subtract 90 degrees. Hold on just a second. 3 plus J2 ohms. 3 ohms goes here. 6 angle 0 degrees, volts RMS goes here. 4 ohms. J2 ohms. All right. So multiplying 3 angle 10 by negative J2 is 100% correct, okay? Negative J2 is the same as 2 angle negative 90 degrees expressed in polar form, right? So if we multiply 2 angle negative 90 times 3 angle positive 10, we get 6 angle negative 80. Because when we multiply two polar form complex numbers, we can simply multiply the magnitudes and add the phase angles. So just to be clear here, I am saying that this negative J2 is the same as 2 angle negative 90 degrees ohms. Everybody okay with that? When we multiply 2 angle negative 90 times 3 angle positive 10, that's going to give us 3 times 2 is 6. And it's going to give us negative 90 plus 10, which is negative 80. All right. Now, Cheston, earlier you had mentioned we could just say that it's negative 6 angle 10 degrees, and then we would have to do something plus or minus 90 degrees. The issue that I have with that specifically is that having a phasor with a negative magnitude doesn't make any sense. So we'd first convert by 180 degrees to make the magnitude positive, and then we have to take into the account J. Whereas in my opinion, if we convert this negative J2 ohm impedance into its polar form representation to do the math, or literally just put it in a calculator, either way is fine. We're going to get this result much more cleanly and with less steps. So that would be my suggestion. Let's call this quantity phasor voltage VA, and this isn't entirely necessary, but I'm going to call my bottom node ground. And so from this, applying KCL at node A, I will have VA minus 12 angle 0 degrees. Sorry, these shouldn't be RMS voltages. We're not there yet. I don't know what I was thinking. Not that it particularly matters, but divide this by 3 plus J2 ohms. Then we're going to have VA over, excuse me, VA minus 6 angle 0 degrees volts divided by J3 ohms plus VA minus 6 angle negative 80 degrees volts divided by 4 minus J2 ohms is equal to 0. So effectively what I'm doing here in this last portion, when I'm adding these currents together, is combining these two impedances into a single equivalent impedance, which eliminates that node point in the middle. Now, if I'm not mistaken, your calculator likely can't even do this, solve this one equation, one unknown system of its own volition. At least I don't think my TI 36s can. So what we'd have to do from here is a little bit of algebra, right? So what I mean by that is we can see that there's a common factor of VA in all of our terms. So I could say that we would have VA multiplied by a factor of 1 over 3 plus J2 ohms plus 1 over J3 ohms plus 1 over 4 minus J2 ohms is equal to 12 equals 0 degrees volts divided by 3 plus J2 ohms plus 6 angles 0 degrees volts divided by J3 ohms plus 6 angle negative 80 degrees volts divided by 4 minus J2 ohms. Everything on the right-hand side is simply a constant. The coefficient of VA is a constant value. And so from this, we can easily solve for the quantity VA. Let's take just a moment to do that. So to me, and just to be clear here, I'm not done yet. This is going to look like 6.081 angle negative 54.067 degrees. And because I'm dividing voltage by impedance, units on this part should be amps. That's what my right-hand side equal to. And I kind of break these down into smaller digestible bits. So I just simply did this math over here. Then I'm going to do this math over here. I'm saving each one of the variables. I'm going to divide the result of this by the result of this so that my calculator can handle it all. 1 over 3 plus 2i plus 1 over 3i plus 1 over 4 minus 2 for that as variable y. That's 0.579 angle negative 41.950 degrees per ohm. And I get 10.499 angle negative 12.118 degrees. That correct? Anybody else get that? So, Sonny, if this voltage VA is correct, how do I determine my current I that I'm interested in? Which I guess I should draw here real quick.
When you just multiply that units, 3 plus j.
So there's a couple of things. Multiplying voltage by impedance doesn't get me current. Dividing the voltage by the impedance. Secondly, what do you mean explicitly by the voltage?
The voltage drop at like VA.
So VA is the potential difference between this point in the circuit and ground, which is not the voltage drop over literally any of the impedances that we have, right? So the voltage drop over the 3 plus J2 ohm impedance is VA minus 12, right? The nodal voltage on the positive polarity side minus the nodal voltage on the negative polarity side, or I'm assuming those polarities because the current, I'm just saying the current flowing into the positive polarity side. Okay. So I, that we're interested in, is simply VA minus 12 angle 0 degrees volts divided by that impedance of 3 plus J 2 ohms. Which I get to be 0.778 with an angle of negative 161.903 degrees amps. So solving that problem in effectively 2 steps, I think that's pretty reasonable. That was a very good suggestion, Justin. How I looked at it, and I legitimately think that might have been a better suggestion. What my original intention to do here was literally disconnect everything to the right of the 12 angle 0 degrees voltage source and the 3 plus J2 ohm resistor and replace it with a Thevenin equivalent circuit so that it'd have a simple single loop circuit that I could solve for the current for easily. But I think solving for the Thevenin equivalent would have taken at least 2 steps, one for the voltage and one for the impedance. So just a simple source transformation and then KCL was actually faster. So very good eye. All right. Let's do something else. So let's say that we have an 8 angle 0 degrees volt source a 4 plus J3 ohm impedance, a 2 angle 15 degrees amp source, and 8 minus J1 ohm impedance. And a 2 plus J9 ohm impedance over here. And our ultimate goal is to find this voltage, which I'm going to call Vx. And just to keep things interesting, I'm going to say, let's not do any source transformations. Because we could absolutely, we have a practical voltage source on the left-hand side, which we could convert into a practical current source. And then the practical current source would allow us to combine this current with this current. We'd have this guy in parallel and this branch over here. It actually take us several steps. But there is a different way to do it that we could take care of it pretty trivially. Anybody have any thoughts what that might be? Anybody remember how to apply? Oh, are you going to raise your? Superposition was where my head was at, but a KCL isn't necessarily a bad suggestion either, right? So if we chose the bottom node to be ground, we found the node, the voltage at this node, we could then do voltage division to get there. So that would be a two-step process effectively. Superposition will get us a two-step process as well. So let's do superposition if that's okay by you. So using superposition with the voltage source on and the current source off, we are going to have the following circuit. ∠0 volts. This guy is going to be Vx prime. This should be 4 plus J3 ohms. This is 8 minus J1 ohms, 2 plus J9 ohms. And hopefully we can all see that just using voltage division, we're going to have 8∠0 volts multiplied by 8 minus J1 divided by 4 plus J3 plus 8 minus J1 plus 2 plus J9, like so. And so, Ian, I'm sure you're already done. What's Vx prime? Oh, no, it's okay. So for a problem like this, personally, I would store this impedance as A, this impedance is B, this impedance is Z, and then just let my calculator take care of all the good stuff. What'd you get, Ian?
3.622.
All right. Anybody else verify that? All right, Brandon shaking his head yes, so let's call it good. Okay. So we now rework the problem with the current source on. So we're going to have a short circuit. 4 plus J3, 8 minus J1, 2 plus J9, 2 angle 15 degrees amps. And let's call this Vx double prime. So there's really two ways we can go about getting this voltage. One is if we multiply this current 2 angle 15 degrees amperes by the combination of 4 plus J3 in parallel with the series combination of 8 minus J1 plus 2 plus J9, we get the voltage drop over everything, and then we could do voltage division. Or we can do current division to find how much current flows through the right-hand branch and then multiply that by the 8 minus J1 ohm impedance. That's the route that I'm going to go. So I can say that Vx double prime is going to be 2 angle 15 degrees amperes times 1 over 8 minus J1 ohms plus 2 plus J9 ohms divided by 1 over 4 plus J3 ohms plus 1 over 8 minus J1 plus 2 plus J9, which is giving me the current flowing through the right-hand side of the circuit. And then I multiply all of this by 8 minus J1 ohms. And current times impedance gives me voltage. So it's going to be 2 angle 15 times 1 over C. If I stored my variables in my calculator correctly, I get 4.528 angle 6.588 degrees. What's my last step here? Combine the results, exactly right. Vx prime plus Vx double prime is equal to Vx 3.623 angle negative 45.28 plus 4.528 angle 6.588 yields 7.341 angle negative 16.255 degrees. All right. Right. So when I add these guys together, 3.623 and 4.528 don't make that, right? So addition is best performed if you were going to do it by hand in a rectangular coordinate system. So it's really hard to say, like, unless these two angles were literally identical, it's hard to say what the magnitude or the phase angle is going to be. So, all right. We've done superposition, we've done current division, voltage division, KCL, Ohm's law in working these problems. Any other DC circuit analysis tech is need a reminder of how to apply, or can we move on to the final topic for the day? Anybody got anything that's not super fresh? All right. So the last thing that I want to talk about today is multi-frequency circuit analysis, okay? And so all that means is, let's say that we have a circuit like this. Let's call this IS of T. Let's say that we have a 5 ohm resistor, 3 Henry inductor, an 8 ohm resistor in series with a 0.2 farad capacitor. And then over here, we have a voltage source, S of T. And we want to know this current IL of T like so. So this is just a standard circuit, nothing wild or crazy here. The wackiness comes now. Let's say that IS of T is 0.5 cosine 3t amps, and ES of T is 8 cosine 5t volts. So this circuit is being excited at 2 different angular frequencies. If we try to just throw this guy into the frequency domain or into the phasor domain, we can easily see that IS would be 0.5 angle 0 degrees amps. VS would be 8 angle 0 degrees volts. But what would the impedance of this inductor be? So the problem with the frequency domain, or working in the frequency domain, is that we have suppressed all frequency terms, meaning that we are working under the assumption that everything is excited at the exact same frequency, okay? When we have excitation at multiple frequencies, which is the case like this, we have to use superposition to work the problem. So as long as our circuit is a linear network, which resistors, inductors, and capacitors are absolutely linear circuit elements, and I hope at this point we've proved that to you, we can simply figure out what the contribution of the source IS is to the quantity IL. We can figure out what the contribution of the voltage source VS is to the quantity IL, and then simply add those two results together. So let's go ahead and do that. So with our current source on and the voltage source off, this circuit is going to look like this guy. All right. So we have 0.5 angle 0 degrees amps. Our 5 ohm resistor is obviously still just a 5 ohm resistor. Our inductor is going to have an impedance of J times omega, which in this case will be 3. So J times 3 times 3 looks like J 9 ohms. Then we'll have our 8 ohm resistor over here. We have our capacitor, whose impedance depends on the value of omega. And then since our voltage source is off, we short circuit it. So let's talk about this guy right here. So we're going to have 1 over J times 3 times 0.2. So 3 times 0.2 is 0.6. 0.6 is 3/5. When we flip that over, that's 5/3. So negative J 5/3, if my math is correct. Like so. Here's our quantity IL prime that we're trying to solve for. So how might we go about determining this quantity IL prime? Current division, absolutely. So we could say that IL prime is equal to 0.5 amps, or 0.5 angle 0, although it doesn't particularly matter if the angle is 0, whether or not I include it, times 1 over J9 ohms divided by 1 over J9 ohms plus 1 over 8 minus J 5/3 ohms. Give me some numbers. While you guys are calculating, I'm going to ask a question. Why doesn't the 5 ohm resistor show up in my equation? Exactly right. So we know for a fact that all of the current from the 0.5 angle 0 degrees amp source is going to flow through that 5 ohm resistor, and then it's going to split. So the 5 ohm resistor shouldn't show up in my current division equation. No, it literally cannot show up in the equation at all. And it's because, as I'm not sure who said it exactly, but since these two elements are in series, the current doesn't have an opportunity to split when it sees the 5 ohm resistor. All of it flows through the 5 ohm. So we know that the current that's entering this node here is half an amp, which is where we get this half an amp. And then the two parallel branches have impedances of J9. So we have 1 over J9 because that's the one we're trying to solve for. And then we do 1 over J9 plus 1 over 8 minus J 5/3 because those are the two branches in parallel. Anybody got a number for me?
0.217 angle
0.217 angle. What was that, please, Ian?
negative 96.8 degrees.
All right. Is everyone okay with this analysis? Anything seem wild or wacky or anything? All right. Now we'll analyze a circuit at T is equal, excuse me, sorry, with the voltage source on and the current source off. Obviously have transient analysis on my mind. Yep. So our current source is going to look like an open circuit. Our 5 ohm resistor is still a 5 ohm resistor. Our inductor now, since our angular frequency omega has changed, the impedance of our inductor should change, right? So J times omega times L in this case is going to be J times 5 times 3 or J 15 ohms. Our 8 ohm resistor stays unchanged. We have our capacitor. So at an angular frequency of 5 radians per second, 5 times 0.2 is 1. So this should just look like a minus J1 ohm impedance. And then this voltage is 8 angle 0 degrees volts. Here's our quantity IL double prime. And we can see easily that IL double prime is just 8 angle 0 degrees volts divided by 8 minus J1 ohms plus J15 ohms. Somebody please give me a numerical answer for that. Pardon?
Wasn't the resistor 3 ohms?
It's like 8 to me.
The first current,
377. All right. 54.27 280. Okay, thank you. Yeah, and that's sorry for my penmanship. So for my current here, I get 0.496 angle negative 60.255 degrees amps. All right. What do I do now? I disagree. So let's talk about why we can't add the phasor representations together. They were both evaluated at different frequencies, so it doesn't make any sense whatsoever to add them together. The expectation here is that since we have sinusoidal excitation at 2 different frequencies, IL should be the sum of 2 sinusoids, one at an angular frequency of 3 radians per second, the other at an angular frequency of 5 radians per second. If we add these phasor results together, how do we know which angular frequency to use? The short answer is we don't. It doesn't make any sense to do that. So I was intentionally trying to trick you guys. Go back to the time domain first and then add the results together. Absolutely right. So that means IL of t is 0.377 cosine 3t minus 54.280 degrees plus 0.496 cosine 5t minus 60.255 degrees amps. So if we excite our network at 2 different frequencies, we should see that our response contains 2 different frequency components. There is no way to combine these 2 together. This is the simplest form that we can find for this. They still have 2 different angular frequencies, right? So how does 0.377 e to the j 3t minus 54.280 plus 0.496 e to the j 5t, et cetera. How do those add? They still don't, right? When we multiply exponential functions together, then we get to add the exponents. But since we're adding exponential functions, we're stuck. This is as simple as it's going to be. Do we need to work another multi-frequency circuit analysis problem, or do you guys kind of get the gist? In short, you have to do superposition. You literally do not have a choice in the matter because of the multiple angular frequencies involved. Using superposition, you find the quantity or quantities of interest, and then you need to go back to the time domain before you combine your results at the end. Okay. If you don't do that, you've made a very significant mistake, which should be obvious when you try to figure out what value of omega to use when you combine those two together. Any other questions or anything? All right, so we're going to knock off about 25 minutes early. I'm going to pop upstairs and put up a homework assignment on this material and all that kind of stuff so that you guys can get cracking on it. I believe what we are going to do on Wednesday's class meeting is instantaneous power and average power, which will be a pretty brief review because we covered those in circuits 1. And then we will cover what's called a maximum average power transfer theorem, which is the maximum power transfer theorem for AC circuits. And we'll spend a little bit of time on that because it's pretty new and it's significantly different than what we did in a simple DC circuit. So I'll see you guys on Wednesday.
Probably worth at the beginning class is that steady state sinusoidal?
Yes.
Okay.
Yes, sir.
Getting ahead of you a little bit, but where did you say like a transient analysis like you were before on RLC circuits, and you excite them at different frequencies? Would they just eventually combine to a common frequency, or would they just completely decompose each other?
So if we go to Desmos or something like that, we can just add these. So they're going to settle to something like this.
Okay. They would both- okay.
Yeah.
I just grabbed it. It looks very.
Yeah.
I love looking at sinusoidal combinations.
Yeah.
Fourier transforms are one of my favorite things just in general.
You're going to like circuits 3 and linear systems and signals next year. Then, because
Yes,
that's a
I'm very
whole
excited.
hell of a lot of that. Yeah. We're going to exploit, like when we talk about filters, everything that we're going to be doing, like filters make sense because if you know Fourier transform, you know that practically any signal can be decomposed into a sum of sinusoids at different frequencies. And then we can easily see that, okay, so we have all of these impedances, which are frequency dependent. So like, for instance, at DC, we know that a capacitor is an open circuit, but at high values of omega, it looks like a short circuit. And for an inductor, it looks like a short circuit at DC, and at very high values of omega, it looks like an open circuit. And so that's going to tell us like what signals get passed and what signals get suppressed depending on where we're taking the voltage drop.